5.1 linear models. Okay, so the rate of change, the change in one quantity relative to the change in another. Okay, when we're talking about rates of change, we usually they require units. Okay, so an example of this is kilometers per hour. So a formula that we can use is rate of change equals. So we always do the change in the dependent variable, so delta y, and that's the one going up the y-axis, okay, over the change in the independent variable, and that's going across the x-axis. Okay, I'm just going to highlight speed, very, very common rate of change used in everyday life. So speed equals distance over time. Okay, example 1. This graph shows the height above the ground of a rock climber over time. Okay, so as you can see in the graph, the rock climber, if we take a look, starts at 25 meters above the ground and then descends. So the rock climber is going down toward the ground. The ground is obviously at 0. Okay, the rock climber is not going into the ground. So you see that the line does not exist in the ground. Okay, calculate the slope of the graph. So the change, we're going to go, the slope is the change in y over the change in x. Okay, so the change in y, as you can see here, he goes from 25 to 0, so it's negative 25, right? He's going down, and then between 0 and 8 seconds. Okay, so what we're going to do is we're going to interpret the slope as a rate of change. Okay, so if we go negative 25 divided by 8, we get negative 3.125. And I'm okay with that, negative 3.125. So if we take the negative 3.125 and we tack on meters per second, right, because rates of change, you always want a unit, we can say the climber descends by 3.125 meters every second. Okay, describe the relationship between height and time. Well, if I'm going to describe the relationship, so as time increases, the height of the climber decreases. Okay, and what is the height of the rock climber when the time is 6 seconds? Okay, so let's change colors. We're going to go to 6, and we're going to follow it up, and we're going to use this line. So if we follow this across, let's say maybe 6 or 7 meters. Okay, so let's say 7 meters above the ground. Okay, example 2. This graph shows the relationship between temperature and altitude. Okay, calculate the slope of this relationship. So again, we're going to go m equals delta y over delta x. This triangle is called delta. You guys might see in movies, maybe like delta, gamma, sigma as a sorority. So delta is just a Greek letter, and it just means change in. Okay, so if we're going down here, we're going to go down. Okay, but we're not going to ballpark this. We're actually going to, let's actually read the x and the y. Okay, so the y's go from 25 to 13. So if you think about it, what we're doing is we're going to subtract those, and we get 12. Okay, and then the x's go from 200 to 2200. So if we subtract those, we get negative 2000. Okay, then we can just divide. And we know that our slope is going to be negative because our graph is going down to the right. Okay, so I get negative 0.123. Yep. Okay, negative 0.006. Interpret it as a rate of change. So we're talking about temperature per meter. Okay, as the altitude, it's like as the altitude goes up, the temperature goes down. Increases each meter, the temperature decreases 0.006 degrees Celsius. Okay, remember this is negative 0.006 over 1, right? So you have to talk about the y value and then the x value. Is the graph increasing or decreasing or constant? This is decreasing for sure. We can see that the graph goes down to the right. Okay, describe the relationship between temperature and altitude. We kind of did up here, but now we can do it generally. So as the altitude increases, the temperature decreases. And we can see this on the top of mountains, how they have snow, but then on the ground, like if you've ever been to a mountain, on the ground, it's very, very hot, but in the mountain, and then it has all the snow at the top. Okay, what is the temperature when the altitude is 0 degrees? So if we actually continue this up, because we want the altitude to be 0 degrees, which occurs here, it's going to be, so this is like right on ground level. It's going to be about 27, maybe 27 degrees Celsius. Okay, example 3. Find the rate of change of each of the following. Okay, the average adult breathes 37 liters of air every 5 minutes. So what is the rate of change in the volume of air? So we represent slope with an M. So we're going to say 37 liters per 5 minutes. And if you divide those out, it's 7.4 liters per minute, which is like per 1. So as soon as you divide these, what we get is a unit rate, and it's like per 1 minute. Okay, this here is called a unit rate when the denominator is 1. And that's what we've been doing so far. A bird flaps its wings is 200 times every 30 seconds. Okay, so if we go 200 times, 200 flaps every 30 seconds, and we divide those out, we get 6.67 flaps per 1 second. That could be maybe like a hummingbird. Okay, and a car travels 768 kilometers every 8 hours. So basically, like it could ask what's the rate of change of the distance of the car, but the other word for this is just simply what's the speed of the car. Okay, so if you divide these, it's 96 kilometers per, and then per hour or per 1 hour, again as a unit rate. Okay, so example 4, I put the note over here just so that we can take a look at it. So it says a rate of change is positive. Okay, that means the quantity is increasing. When a rate of change is negative, the quantity is decreasing. And when the rate of change is 0, the quantity is constant. Okay, so Let's take a look at this. Example 4. If you work 1 hour and you make $10 per hour, just as an example, try to change this to blue. There we go. Okay, then if you work 2 hours, you would make $20, right? If you work 3 hours, you'd make $30. If you work 4 hours, you'd make $40. And if you worked 0 hours, you would actually just make $0. Okay, interpret the slope as a rate of change. So you make $10 per hour. Okay, include units, that's the dollars, and then that's the hour. Okay, is this trend increasing, decreasing, or constant? This is constant. When we're talking about lines, we're talking about like your wage is not going up. You don't make $10 on the first hour and then 15 and then 20, and it doesn't accumulate like this. It's simply $10 an hour, so that's constant. Okay, so we're going to describe the relationship between earnings per hour and the number of hours worked. Well, as the number of hours worked increases, your earnings, or the earnings increase as well. Okay, so we're going to touch on first differences. So we're going to fill this out. We did a couple of these numbers here. So in 0 hours, you earn $0, 1 hour 10, 20, 30, 40, 50. And we can pattern like that, no problem. That's how you know it's a line. Okay, so just to remember, first differences are when you take the numbers in the Y column, here we go, and you subtract them. So 50 minus 40, we get 10. 40 minus 30, we get 10. 30 minus 20, we get 10. 20 minus 10, we get 10, and then 10 minus 0, we get 10. Okay, this one's just going to be blank. So if we take a look at all the first differences, we can say when the first differences are the same, we have a line. Okay, example 5. Sandra works for $15 an hour. So first, write a formula for the amount that Sandra earns. Okay, so her earnings are $15 per hour. Okay, the E represents the earnings, and the H represents number of hours worked. Okay, so if she works 0 hours, we could take that equation and we could sub in the 0. So then we'd get 0. We could take that equation and we could sub in 1, and we would get $15. We can take that equation and we can sub in 2. So after 2 hours, she'd get $30. We can take that equation and we can sub in 3. 45. Okay, and we can go all the way down this column. Okay, all we would be doing is 15, oh, that's supposed to be 4, 15 times 5, 15 times 6, 15 times 7, and then 15 times 8. Okay, 45, 60, 75, 90, 105, 120. Okay, and if we wrote these as ordered pairs, we would write 0, 0, 1, 15, 2, 30, 3, 45, 4, 5, 6, 7, 8, all the way down, comma, and then this column here, 60, 75, 90, 105, 120. Okay, and then that's how we get the order pair. So you just take the equation, if you're given it, or you can create one, and then all you do is sum in different values, and then this acts as a like a T-chart, like a table of values. We come over here to Sandra's earnings on the x-axis or the h-axis. So we call this age. Okay, hours worked, number of hours worked. And then on the y-axis or the e-axis, earnings. Okay, and then we can plot. And because this goes directly from 0, I put very nicely that the axis goes up by 15 because Sandra earns $15 an hour. So we can simply just go up by 15 each time. And that's how we would graph it. Okay, last example, example 6. Pete's Pizza charges $9 for a large pizza with just tomato sauce and cheese. So that's like your base pizza, no toppings. Okay, it costs $1.50 for each additional topping. So this is a little bit different from the last example that we saw with the earnings, because now no matter what, you have that base fee. There we go. Okay, of $9, and then you can add on $1.50 each time. Okay, so what we're going to do is we're going to complete a table of values showing the cost of the pizza up to 6 additional toppings. So pizzas start at $9, no toppings, and then it goes to $10.50, and $11.50, $12, and then $13.50, and then $15, and then $16.50, and then $18. Okay, and all we did here was we started at $9 and we added $1.50 each time. Okay, so let's go ahead and graph that. Okay, this is going to be the cost of a pizza. Okay, this is T, the T-axis, number of toppings. And then this is going to be, oh, sorry, this is the n-axis. This is going to be the c-axis, which is the cost. Okay, so if we're going up here, we're going to start at $9, which is a little bit different than what we saw before. So $9, and then we go up to $10.50, and then $12, and then $13.50, and then 15, 4 toppings, and then the next one is $15.50, and then the next one is 18. So right, that's $16.50. That's why it's a little off. Okay, and then we can connect those, put an arrow on it. Okay, C, does this situation represent partial or direct variation? So this is called partial variation when it doesn't go through 0, 0. Okay, not a huge focus in this course, but this is a partial variation. Okay, starts at $9. Okay, so there's that flat fee. Okay, what is the constant of variation? This is another word for slope in case you see it in your textbook. Okay, what is the slope? What does it represent? Okay, so the slope is $1.50. That's what we're going up by. Okay, and it represents the price per topping. Okay, and then what we can do is we can use the graph to estimate the prices of a 9-topping pizza. So if we go to 9 and we follow this up, and on this quite difficult because it's so small, but it's going to be $22.50. going to be about here. Okay, so if you drew a really nice big clear graph with a ruler, then you're going to be able to extrapolate for the 9 toppings on a pizza.